So a diode is a two-terminal electrical component that utilizes a rectifying junction, so either a PN junction or a rectifying metal semiconductor junction that conducts current primarily in a single direction. So diodes can be thought of as kind of a one-way valve for current flow in a circuit. Our diode schematic symbol is this guy. So this is our diode, and this terminal is our anode, and this terminal is our cathode. So if we have a voltage drop VD like so, this is our direction of current flow ID. So effectively, current is flowing in the direction of the way the triangle is pointing. And the vertical line there is the negative polarity terminal of the diode. That's how you can tell which way is what. So current always flows in the direction that the triangle is pointing. And the big horizontal, or excuse me, vertical line in this case is our negative polarity terminal. All of the other two-terminal circuit elements that we've dealt with, at least in the classes that I've taught you guys, have been linear circuit elements. So resistors, capacitors, inductors, and all that kind of stuff, they behave linearly, which means that the voltage and current are proportional. That constant of proportionality could be something as simple as a resistance value, or it might be the capacitance times a derivative, or might be an integral-based relationship, but all of those are linear operations, which I think at this point in your 321 class, you should have come to know that. Diodes are nonlinear circuit elements, meaning that there is no simple proportional relationship between current and voltage. So to overcome that nonlinearity, multiple different models have been developed that we can use to analyze diode circuits. All right. The first model that we are going to talk about is the Shockley or exponential diode model. So the Shockley model utilizes the relationships that we developed for rectifying junctions in our physics background lectures over these last couple of class periods. So our Shockley diode model says that our diode current ID is the cross-sectional area A times JS, which is our reverse bias saturation current density that we developed for both PN junctions as well as rectifying metal semiconductor junctions, multiplied by a factor of EXP to the VD divided by VT minus 1, where VT is nothing more than our thermal voltage, kBT over Q. Okay. So this matches literally exactly what we derived for PN junctions and metal semiconductor junctions. If we consider the product of the cross-sectional area times that saturation current density to be a quantity IS, known as the saturation current, or oftentimes called the scaling current. And the reason why it's called the scaling current is because it's proportional to the cross-sectional area. So that if we have multiple identical diodes, meaning that they're all doped the same way and all that kind of stuff, the current scales as the area goes up. So, for instance, if we had the following part of a circuit, let's not even call it a full circuit, where we had two diodes connected in parallel. Let's call this guy diode 1, this guy diode 2. We have some total current, I total, flowing into our parallel diode network, and the area of diode 1 is 4 times the area of diode 2. What portion of our total current will flow through diode 1 and what portion will flow through diode 2? Anybody have any thoughts?
4/5 go through diode 1, 1/5.
Exactly right. It's effectively current division for diodes. So instead of based on a resistor value, it's based on the cross-sectional area. So that's 100% correct. We know, that IS1 will be exactly equal to 4 times IS2, and therefore ID1 will be 4/5 times I total. ID2 will be 1/5 times our total current. Unfortunately, the overwhelming majority of the analysis that we are going to do in this class will not be nearly that easy. Was that a boo? So let's take a look at an actual circuit that has a diode in it and not just a part of a circuit, and kind of go through some things here, all right? So let's say that we have a 1 milliamp source connected in parallel to a resistor R, connected in parallel to 2 diodes in series. So let's call this guy D1. Let's call this guy D2. We are told that IS1 is equal to IS2 is equal to 0.5 femto amperes. Who knows what a femto anything is? 10 to the negative 15. So that's 5 times 10 to the minus 16 amps. We are also told that IR, the current flowing through the resistor direction down, is 0.3 milliamps. And we are told to assume that VT is equal to 26 millivolts. So effectively the circuit is operating at room temperature. We want to find the value of that resistor R. Anybody have any inkling of an idea on how we might approach something like this? So this is our first real diode circuit where we're going to have to put circuit analysis tools into play. Finding the current through the diodes. Okay, so Preston suggests that there will be some diode current. I'm going to call this guy ID1, and this current right here, ID2. I tend to agree with him. We can find out what that diode current is by applying Kirchhoff's current law, because even though this is a nonlinear circuit, Kirchhoff's current law, Kirchhoff's voltage law, Ohm's law, all that kind of good stuff is going to apply. Really, the only things that we can't do with a nonlinear circuit are superposition principle, because that depends on linearity, and the application of Thevenin and Norton equivalent circuits also depend on having some linearity. So KCL, KVL, and by extension, mesh analysis, nodal analysis, all that stuff are fair game. Superposition, we can't do, which you guys never seem to care to do anyway. And then Thevenin and Norton equivalent circuits are also out the window. All right, so by applying Kirchhoff's current law, we should easily be able to see that our diode current ID1, which has to be equal to ID2 because they represent the same current flowing through that right-hand branch, is going to be equal to 1 milliamp minus 0.3 milliamps, or 0.7 milliamps. So we know our diode current. What do you think we should do next? Any thoughts? Use the current to find the voltage. Okay, that's fair. So since our diode is carrying a non-zero current, there must be some voltage drop VD1 over diode 1 and some voltage drop VD2 over diode 2. And we should expect these voltages to be identical because both diodes have the same saturation current and they're both carrying the same amount of total current. So VD for both should be the same. So let's revisit our equation, our Shockley diode equation, okay, which says that ID is equal to IS multiplied by the exponential of VD, our diode voltage, divided by VT, our thermal voltage, minus 1. This equation simplifies to IS EXP VD over VT. Effectively, we're throwing away the minus 1 bit when our diode current ID much greater than our saturation current. Are we under such a condition? Absolutely, right? Our diode current is on the order of 10 to the minus 3 amps. Our saturation current is on the order of 10 to the minus 16 amps. So we are somewhere in the ballpark of 1 billion times larger. So I feel very strongly that that satisfies the much, much greater than condition. So we can take this simplification here and do a little bit of manipulation, right? So if I divide both sides of my equation by IS, I will have ID divided by IS is equal to the exponential of VD over VT. If I take the natural log of both sides, then that's going to give me VD divided by VT is equal to the natural log of ID over IS. And so I can just multiply both sides through by a factor of VT. And this lets me determine my diode voltage as a function of current under the condition that ID is much greater than IS. And an alternative way to state that condition is that VD, our diode voltage, is assumed to be greater than our thermal voltage. So it works either way. So using that, we could say that VD1 is equal to VD2 would be 26 millivolts times the natural log of 0.7 times 10 to the minus 3 amps over 5 times 10 to the minus 16 amps, which will give me a voltage of 0.727 volts. From this, we can easily see that our voltage VR is just twice VD1 or 1.454 volts. And therefore our resistance R is just VR over IR or 1.454 volts divided by 0.3 milliamps is 4.848 kilo ohms. Anybody have any questions on that analysis? Logan.
Is it VR is equal to these VDs? Each particular diode has the 7.7 volt.
Exactly right. So if these were not identical diodes, so let's say if we had diodes here where each of them had a different saturation current, then we couldn't do that because we would have two different diode voltages that we would have to add together, right? Kirchhoff's voltage law around the right-hand loop tells us that our resistor voltage, positive polarity on top, is simply the sum of those diode voltages. The fact that we're using identical diodes lets us just double the diode voltage for one of them. But if we had non-identical diodes, meaning that their saturation currents were different, then we would obviously have different voltage drops over each individual diode in that chain.
And so the only change would be in our natural law, you change the saturation current.
Exactly right. So if we had two different saturation currents, the voltage drop over diode 1 would be dependent on the saturation current of diode 1. The voltage drop over diode 2 would be dependent on the saturation current of diode 2. But both of the diodes would still have to carry the same diode current ID because they're connected in series. All right, so that's just good old Kirchhoff's current law. Two things are in series, they have to carry the same current. All right, so this is another example where the circuit analysis was, I don't want to call it trivial, definitely not as trivial as the first one, but straightforward. Let's take a look at something a little bit more robust. So let's say that we have the following circuit where we have a 10 ohm resistor, a 1/2 amp current source, a 50 ohm resistor, a diode, a 10 volt source, and then a 25 ohm resistor down here. The positive polarity of my diode voltage will always be on the triangle side. The negative polarity of my diode voltage will always be on the line by itself side. And so our expectation is that our diode current ID will flow in this direction. So our goal in analyzing this circuit is to figure out what ID and VD are. So any thoughts on how we might approach this guy? Mesh, okay. Let's give mesh a whirl. I'm gonna have a current I1 up here on top. And I'm gonna have a current I2 here on bottom, okay? So we can pretty easily see that we'll have a current relationship equation that says our diode current, sorry, that's not correct, our current I1, my apologies, is equal to 1/2 amp. And if we apply Kirchhoff's voltage law around mesh 2, we'll have negative 10 volts minus VD plus 25 ohms times I2 is equal to 0. So I have two equations and effectively three unknown quantities right now. So how are we going to fix this? All right. So we can get another effectively current relationship equation here that says that ID is equal to I1 minus I2. So I'm going to put that as 0.5 amps minus I2. And we could rearrange this guy and say that I2 is equal to 0.5 amps minus ID, if I did my algebra correctly. And substitute that relationship in right here, which would yield negative 10 volts minus VD plus 25 ohms times half an amp minus ID equal to 0. And I'm going to do a little bit of algebraic manipulation here. Negative 10 minus VD plus 25 ohms times half an amp is equal to 25 ohms times ID. And thus we see, let's see, so we're going to have negative 10 plus half of 25. So negative 10 plus 12.5 volts looks like 2.5 volts minus our diode voltage VD divided by a 25 ohm resistance is equal to ID. All right, so there are two different ways that we can get a value for VD and ID. The first way, which is talked about in your textbook, is a graphical analysis, where effectively we would plot this function and our Shockley relationship on the same axis and see where they intersect. That's what's called load line analysis, and I haven't seen anybody actually do that since Dr. Cox taught me this crap the better part of 20 years ago. So we're not even going to bother with that hippy dippy figuring out what the intercept point on two graphs is. It takes too damn long. The other method is using an iterative method where we assume a value for VD, which gives us a value for ID, and then using the value of ID, we recalculate VD and just kind of loop back and forth until we settle to a particular answer. Okay. So it is tedious, but it is not nearly as tedious as doing it graphically. So that's what we're going to start off with. All right. So for iteration number 1, let's make a guess for VD. I personally chose half a volt when I did the iterative method for this, but it really doesn't matter what we choose. So if you guys want to choose something else, we can do that, and we'll see that it's still going to resolve in roughly 3 to 4 iterations either way. So do you want to work with half a volt, or do you want to come up with something different and just see what the hell happens? Half a volt? Okay. So if we guess that our diode voltage VD is half a volt, then we can see that our diode current is simply going to be 2.5 volts minus half a volt divided by 25 ohms gives us a diode current of 80 milliamps. And for iteration number 2, what we would do is say our diode voltage VD is 26 millivolts, our thermal voltage, times the natural log of ID, which is 80 milliamps, divided by, okay, so this is something that's pretty important here. I forgot to mention to you guys what the value of I sub S is, which is critically important to doing this iterative method, so I apologize. In this particular example, we're going to say that IS, our saturation current density, is 5 nanoamps. Also, we're going to explicitly state to use the thermal voltage value of 26 millivolts. That's usually going to be what happens, but it's nice to be told what to do. So I apologize for forgetting to include that portion. Wesley. Yeah, so if you're not told what VT is, just assume that it's 26 millivolts. Assume that you're operating at a temperature of 300 degrees Kelvin. Sure. You can't really assume a value for IS though, because it's going to change vastly depending on whether you're using small signal diodes, which typically have saturation current densities on the order of pico to femtoamperes. This would be kind of a medium signal because it's in the nanoamp range. And for high power diodes, it could be in the milliamp range. So I apologize for forgetting to better specify our problem here. So circling back around, 80 milliamps divided by 5 nanoamps. And that's going to give us a value of 0.431 volts. So we had a change in voltage of around 70-ish millivolts. So that's a pretty big change. So we'll now calculate ID using this value, 2.5 volts minus 0.431 volts. They moved on me. Divided by 25 ohms gives us a current of 82.748 milliamps. So only a change of around 2 milliamps here. So we're probably pretty close. Iteration number 3. We would say that VD is 26 millivolts times the natural log of 82.748 milliamps divided by 5 nanoamps, which gives us a voltage of 0.432 volts. So our voltage only changed, let's see, so that would be 1 microvolt, I believe. No, 1 millivolt, I'm sorry. Our voltage changed 1 millivolt there. So not a big change, so we're probably looking pretty good. And just for the sake of argument, recalculating our current ID would be 2.5 volts minus 0.432 volts divided by 25 ohms gives us 82.713 milliamps. Now we could continue iterating on this if we wanted to. But the change in the voltage that we saw between these last two steps is literally a millivolt. The change in our current is somewhere in the ballpark of 35 microamps. This is a pretty good stopping point. Generally speaking, 3 to 5 iterations is all you should ever need for a diode circuit. Okay, it should settle pretty quickly. It shouldn't matter. It literally shouldn't matter. Now, that being said, at the end of this class period, we are going to talk about what's called the constant voltage drop diode model. And in a constant voltage drop diode model, we assume a fixed value for the voltage drop over a diode. And that depends on the material that the diode is made of. So for a silicon diode, we usually say that it has a voltage drop of 0.7 volts. So that would be a good place to start if you wanted to get a more accurate answer here. For a germanium diode, we would start at 0.3 volts. And for a gallium arsenide diode, we'd start at 1.2 volts. Those values will make a little bit more sense once we talk about what exactly that diode model is and where it came from. But for now, those are reasonable guesses. That being said, it doesn't matter. As long as you assume a positive voltage, you'll get there in 3 to 5 iterations. Mr. Steen.
So is there not a
So you have to do it numeric. It's either numerically or graphically. Now, what I want to point out, and we'll do this in just a moment. So this is how you would do this by hand. Your calculators can all do this using your numerical solver tool. The problem being there is that you can't use your 2x2 matrix or anything like that. You have to get it as an expression of a single variable for your calculator to be able to take care of it, because it can't analyze matrices that have exponential functions and natural logarithmic functions as coefficients in there. It just freaks it out. So, good question. Let's go back to our initial equation here. I'm going to put a box around it. Actually, how do I select? There we go. So I'm just going to take this guy and come down here. And let's draw a line here, right? So how do I get this guy to be a function of a single variable? Well, I know that ID could be replaced with sorry, that's not right. IS EXP VD over VT. So now, if I say that this part is equal to this part, and I put it in the numerical solver of my calculator, it will be able to solve for what VD is that satisfies both sides of that equation simultaneously. Your calculator is doing the iterative process that we are doing. It just does it way faster, but it's literally doing the exact same thing. But we have to give it in a one equation setup that's constrained to some constant value, which is what would happen if we moved stuff to the other side of the equation. Right? So the reason why I purposefully went through and did it with the hand iteration method is because sometimes your calculator literally will not be able to solve these equations. It will still converge within 3 to 5 iterations when you do it by hand, but for whatever reason, just some constraints, your calculator will just say, I don't know, I give up. And you need to be able to do this kind of stuff on an exam or all that kind of good stuff. So I wanted to illustrate the way to do it by hand first, and then illustrate how to do it using your calculator, which is just simply putting at it. So for those of you who know how to use the numerical solver on your calculator, throw this guy in and tell me whether you get something really close to this result for VD. Help if I typed it in correctly. And in your calculator, or at least in my calculator, I have to put in an initial guess value for it to iterate on. Oh. What did I put in? Sorry, it's giving me 2.5 volts, which makes me wonder what I put in incorrectly. Oh, I put in natural log, not exponential, that's why. Oh, that's blah, blah, blah. Yeah, so I get 0.432157, et cetera, volts. So it gives us the same answer. It does it slightly faster depending on how quickly we can plug stuff in and all that kind of jazz. So for this one, it converged pretty easily. But again, that's not guaranteed. I'm not going to intentionally give you something to where you're going to have to do it by hand. But it could happen just depending on how your calculator decides to approach it, how you put stuff in and all that kind of jazz. So I just wanted to make you aware of how this guy works. So that is the Shockley model. Any questions on the amount of analysis involved in applying it? Grace?
Just a question for one. So if we learn, how do you want to show us?
Derive the equation that you're using, and that's good enough for me. Yeah. That's all I could ask you to do. Yeah, so you don't need to go through and just, BS your way through 5 iterations or whatever, just for my sake. Don't, if you're using a calculator, say, I use my calculator, set the equation up and say, used my calculator and got this result, and I'm happy. All right, any other questions regarding the Shockley model here? Okay. So the application of the Shockley model is the most accurate with regards to getting a result, but it's pretty tedious to use, right? So there might be times where we just kind of want a quick and dirty estimate of how the diode is behaving, and that brings us to our next model. Our next model is the ideal diode model. So the ideal diode model treats a diode as if it is a unilateral valve for current in a circuit. Meaning that if the diode is forward biased, it just lets whatever current that needs to flow through flow. And if it's reverse biased, no current flows through. So we are approximating our, this is ID. This is VD. So our Shockley model gives us something like this. Right? Our ideal diode model is going to look like this from a current voltage perspective. Here's ID. Here's VD. So it's no current when we are reverse biased and effectively up to an infinite amount of current when we are forward biased. So what we are doing is we're taking our diode and under forward bias conditions, saying that it looks like a short circuit. So we're saying that our diode current ID will be greater than 0. Therefore, our diode voltage will be, as an estimate, 0 volts. And under reverse bias conditions, we use an open circuit. So we're saying that VD, our diode voltage, will be less than 0. Therefore, our diode current will be 0. And we use this approximation because for a couple of thermal voltages, like if our reverse bias voltage is a couple of thermal, a small multiple of our thermal voltage, our current should saturate to effectively just what IS is very, very quickly, which is going to be very, very small for most applications, near 0. So we're just going to say it's 0. And for forward bias conditions, we should see that when our voltage is a couple of more positive than a couple of thermal voltages, the current is just going to increase very rapidly. And so we are very lazily saying, well, let's just treat it as if as soon as the diode turns on, any amount of current that needs to flow through can flow through. Okay. So this is, again, just a quick approximation to figure out what's happening. So this is a good initial estimation. It is not particularly accurate, but it is very fast to see what's happening. Okay. So let's look at that same problem again, and I'm going to intentionally assume that the diode is off as my first state to show you guys how you interpret the results. Wesley. 0. Yeah, so if it's forward biased, so if we are assuming that the current flowing through the diode is positive, we say that there's no voltage drop across the diode. So we don't have an estimation or anything. We're just saying it's 0. All of the current is passing through because this guy happens to be forward biased, or none of the current is passing through because this guy happens to be reverse biased. So if we apply the ideal diode model to our example that we worked, let's start by looking at it with diode D1 is off. And off means that we're in a reverse bias condition. So we'll have 10 ohms, half an amp up here. $50 ohms goes here. Our diode voltage will always have the polarity to where the positive polarity terminal is on the cathode. Hold on, make sure I'm not saying that backwards. Anode side. And then the negative polarity terminals on the cathode side, always, always, always. Then we have our 10-volt source down here. Our 25 ohm resistor here. All right. So if we do Kirchhoff's voltage law around our bottom loop, what we will observe is that negative 10 volts minus VD plus 25 ohms times half an amp is equal to 0. Everybody okay with that KVL equation? And so from that, we see that VD, our diode voltage, is 2.5 volts. We can tell that this is a wrong assumption because our diode voltage is positive. If we are assuming that our diode is off, the voltage drop over the diode needs to be negative. If it is not negative, we picked wrong. Okay? So if we rework the problem and we assume that the diode were on, it would look something like this. Our diode current will flow from the positive polarity to the negative polarity. And so how do you think we'd go about figuring out what that diode current is in this case? Not just going to be a simple application of Kirchhoff's voltage law this time. It's going to require a small amount of thought. Not a whole hell of a lot, because this is just a very simple DC circuit that you guys should have been able to do 3 or 4 days in the circuit one, but maybe it's been a minute. How do you think we're going to do this? Pardon? I mean, if you want to brute force it by doing mesh, you could. I would argue there's maybe a little bit easier way to do it than that. Superposition is too much work as well. All right, let me ask you guys a question. What's the current flowing through the 50 ohm resistor? What's the current flowing through the 25 ohm resistor? Did I hear 0? Did I hear 10 times 25? That scares me more than 0. Ohm's law. There's a 10 volt drop over that resistor. There's 25 ohms for the resistor. So 10 over 25 is 0.4, right? You guys really not see that the 10 ohm resistor and the 25, or excuse me, the 10 volt source and the 25 ohm resistor are in parallel? If you don't, well, you have your work cut out for you in this class. All right, so assuming I'm right here, I'm right. How would we figure out what ID is? 0.5 minus 0.4 or 0.1 amps. So because our diode current is positive, that lets us know that we made the correct assumption. Okay. Now it is obviously a binary decision, meaning that as soon as we found out that it wasn't off, it had to be on. But if we had made this as an initial guess, this would let us know that we chose correctly. How does this work as a analysis tool? Well, this is saying that our diode current is 100 milliamps, and our Shockley method told us that it was somewhere in the ballpark of, I think, 84 milliamps. So it's not horrible, but it's not great. Let me double check that. Yeah, 82.7 milliamps. So it's off. It's about 125% higher than it needs to be for this particular, or excuse me, it's about 25% higher than it needs to be for this particular example. So this model is for quick and dirty analysis. Okay, it is not remotely used for accuracy. It is used particularly in multi-diode circuits, to tell you which ones are forward biased and which ones are reverse biased, and then you can use that as a starting point to do some sort of other analysis. Okay. So let's look at another circuit. We have a 5 kilo ohm resistor, some diode V1, an 8 kilo ohm resistor, some 10 volt source, 4 kilo ohm resistor down here, and a second diode for this orientation, which we will call D2. And our goal in this problem is simply to determine whether D1 is on or off and whether D2 is on or off. So we want the right combination. So since there are 2 diodes, there are exactly 4 combinations that we could get, that we could potentially have to go through, okay? So, Bailey, do you want to guess that diode 1 is on or off? Just does not matter. Just literally pick one or the other. Diode 1 is off, all right? So case number 1, D1 is off, and D2, Luke, is diode 2 on or off? Off, all right? So before I redraw it, I want to be clear about this. We are assuming that the diode voltage VD1 will have this polarity. The diode voltage VD2 will have this polarity. Our diode current ID2 flows in this direction, and our diode current ID1 flows in this direction. Because we are assuming both are off, for this to be true, VD1 needs to be negative and VD2 needs to be negative. So if we find that either of these diode voltages are positive, we have made the wrong choice somewhere. Now, what's kind of crappy about this is that if we get it wrong for one and right for the other, that doesn't mean we can simply switch the one we got wrong and be guaranteed to be correct. Unfortunately, it does not work that way. All 4 of the different permutations here are equally valid. But as you gain more experience looking at these circuits, you'll kind of be able to intuit it, which ones you have a good idea of should be on and should be off, so that you won't have to go through all 4 permutations, or heaven forbid 8 permutations if I give you a 3 diode circuit every single time. So I'm going to redraw my circuit with both diodes off, meaning that I am replacing them with open circuits. This is at least one of the easier combinations to analyze. Not that this one's particularly hard because it's not a difficult circuit. So this is my voltage VD1. This is my voltage VD2. So what's VD1? Is there any current flowing in this circuit? No. What's VD1? 6 volts. Which is an incorrect guess because it's positive. Just for the hell of it, what's VD2? KVL around the outside loop. -4, based on the polarity, right? So we would have 10 is equal to 6 minus VD2. So this iteration does satisfy this condition, meaning that the assumption that VD2 was off was correct for this, but that does not mean it's correct overall. It just gave us a value here that meets our criteria, okay? All right, so that combination is wrong. Annabelle, what do you think the state of diode 1 is? Diode 1 is on, okay? And Bell, what do you think diode 2 is? Is it on or off? You think it's on? Off, okay. So our expectation here is that ID1 is positive and VD2 is negative. If both of those conditions are met, we guessed correctly. So here's our 6-volt source. Here's our 5 kilo ohm resistor. We're saying that diode is 1 is on, so we replace it with a short circuit. We're saying that diode 2 is off, so it's still going to be an open circuit. Negative VD2 plus ID1, like so. All right, so what's ID1 going to be? That's a 5, not a 6. There we go. Yeah, I'm blaming that on my handwriting. Yeah. So 6 volts over 9 kilo ohms is 0.667 milliamps. So is our guess that diode 1 is on good or bad? Good, because our diode current is positive. Let's see, then we have VD2. What's that going to be? So I hear -4 and I hear -10, which is correct. -10 is correct, right? So 10 minus VD2 is equal to 0. Sorry, -10 minus VD2 is equal to 0. So VD2 had to be -10. Doing KVL around the right-hand loop. That guess was also good. So diode 1 being on and diode 2 being off is the correct set of states for our diodes. Is it clear to everyone how to do this analysis? Okay, because I'm going to ask you to do it multiple times, homeworks, exams, all that kind of stuff. Mr. Martin.
Another question. Are you ever gonna have a situation where
No, literally never. It cannot happen that way. It will only be one combination that will satisfy all of your diode voltages for on will be positive, and all of your diode all of your diode currents for on will be positive, and all of your diode currents, all of your diode voltages for off will be negative. That will only happen for one permutation. Yeah, so now you don't have to say, well, both of these are correct, so which one is really correct? Does not happen. It's always a single individual correct solution. All right, so ideal diode model, not super great for actual analysis, very, very useful for determining the state of a diode. All right. Our last model, we have 10 minutes to go through this, so we will do it pretty quickly, is the constant voltage drop model. So the constant voltage drop model is just a compromise between the Shockley or exponential model and the ideal diode model. So graphically, if we compare it to our Shockley model, where this is VD and this is ID, our Shockley model looks something like this. Our constant voltage drop model is an approximation that just uses a piecewise linear function. So for our constant voltage drop model, we are going to have some voltage VD on that is called the turn on or cut in voltage for our diode. And effectively all that means is we need to be at this voltage for it to start conducting. Okay. And so our model is going to look like this. So we have no current until we hit that VD on value, at which point any current that needs to flow through the diode can flow through the diode. Okay. So we're approximating that exponential growth as a straight line that's just been moved out some so that it's not occurring directly at the origin. All right. So under forward bias conditions, we are replacing our diode with a battery. So we're saying that ID is greater than 0 and VD is exactly equal to VD on. Under reverse bias conditions, we still get an open circuit. So for VD less than VD on, ID is exactly 0. The constant voltage drop diode model is really nothing more than the ideal diode model in series with a battery. We're saying if our diode is on, we're going to have some voltage drop over it, and then whatever current needs to flow through can flow through. If it's off, we have an open circuit. And it's literally nothing more than our ideal diode model in series with a battery. All right, let me put RB here for reverse bias. So last thing I want to do today, just real quick, let's rework that very first example problem where we assume that our, not the very first, so the first problem that we actually did any real analysis on, the one that we did mesh on, where we were assuming that we have a germanium diode. Oh, and I should write this down for you guys, although I will provide it to you on any exams and all that kind of good stuff. This is our semiconductor material. These will be what we'll use for VD on. For silicon, it'll be 0.7 volts. For germanium, it'll be 0.3 volts. And for gallium arsenide, it'll be 1.2 volts. So for our circuit, half an amp here, 10 ohms here, 50 ohms here. We're going to replace our diode with a battery. And I'm going to use 0.3 volts. I'm just saying arbitrarily that's a germanium diode based on the fact that it has a reasonably large, or it had a reasonably large saturation current when that mattered. Sorry, that should be ohms, not volts. How would we go about calculating our diode? We don't need to test whether this is the correct configuration because obviously when we tested with the ideal diode model and said it was off, it didn't work. That's going to give us the exact same result. So there's no reason to go through that again. So how do we figure out this diode current ID? Killing me. KCL, right? So what's this current I50? 0.5 amps still. This current I25 is going to be slightly harder, but not by much, right? The total voltage drop over the 25 ohm resistor is just this voltage plus this voltage, or 10.3 volts. Over 25 ohms is 0.412 amps. And so from that, our diode current is half an amp minus 0.412 amps is 88 milliamps. So it's kind of a best of both worlds thing, right? We can use it to test whether or not diodes are on or off, and we get a better approximation of what the actual current flowing through the diode is than we got by just using the ideal diode model. So this is the guy that we're going to use pretty much the entire time we talk about the various applications of diodes, because we don't have to get into the crazy complex math of carrying around exponentials all over the place. We'll still get a good idea of how and what the diode is actually doing. All right, so our next class period will be on the small signal diode model. These are our 3 large signal models, and then we'll get into the application. You're going to see that I'm not going to ask you guys to do a whole hell of a lot of this style of conventional circuit analysis, because diodes are actually used for things, lots of very interesting and important things, and I'd rather spend our time talking about what those applications are than just doing circuit analysis for the sake of circuit analysis. So, all right, see you guys on, what day of the week is this? Wednesday? See you on Friday. We are going to talk about that. So a diode can be used as a rectifier, and what that means is that it converts AC signals into DC signals under certain conditions. So that's going to be one of the things that we talk about on Friday. Yeah. That's a very good question, and it's going to, I don't want to say confuse a lot of you guys because it's not particularly confusing, but it's going to be annoying thinking about it. But it's not that bad.